So most of the problems we are using dimensional analysis. For dimensional analysis, we have these things, the relationships which we call conversion factors. So this would be milliunits per unit, so milligrams per gram, or milliliters per liter. And so we have these. This one will convert from like grams to milligrams, or liters to milliliters. This one converts milliliters or milligrams to grams or liters. And so centi, not so much kilo, we use a lot. And so we just string together one or more of these conversion factors to solve some problems. And so this was the mass conversion, which we looked at. But some things are not via conversion factors. And that's a case where we have the zeros mismatch. And so let me go back to this slide here just for a moment. Let's say this is 1,000 milligrams per gram. So the situation here is this. Let's say I had 0 grams of sugar. If I had 0 grams of sugar, how many milligrams of sugar did I have? I had 0. And so that's a case where the zeros match. If you have 0 grams, you have 0 milligrams. Let's say I have to travel 0 meters. If I have to travel 0 meters, how many kilometers do I have to travel? 0. I don't have to move. And so that's another case where the zeros match. But let's say I have 0 degrees Celsius. Does that mean I have 0 degrees Fahrenheit? No, they're mismatched. The zeros are offset. When the zeros are offset like that, I have to add a correction factor, and that correction factor is plus 32 or minus 32. And so that's the case when we have to use an algebraic equation. We have to use an algebraic equation in scenarios where the zeros mismatch, like these. In these 3 scenarios, the zeros mismatch. So for Celsius to Kelvin, it's offset by 273, but the degrees are the same magnitude, the same size. And so if it's offset by 273, then if I want the Kelvin temperature, I just take the Celsius temperature and add 273. So over here, I take the Celsius temperature, 100, and add 273. I'll have the Kelvin temperature. And that's because the size of 1 degree Celsius is exactly the same as 1 Kelvin. So those are matched. It's just the offset in the 0 points. And we have to enter correction factor. That's the algebra correction here. Well, there's one problem over here, and that's this. If the temperature increased by 1 degree C, would that be equivalent to a 1 degree Fahrenheit temperature increase? No. And that's because a Celsius degree is bigger than a Fahrenheit degree. In fact, do you know how much bigger it is? It's 9/5 bigger, or 1.8 times bigger. So for every degree Celsius temperature increase, I have a 1.8 degree Fahrenheit increase. So in other words, the Celsius is a bigger jump. And so I have this European car, and I can set the temperature, but the temperature of the knob just clicks. So I can click by 1 degree, but it's not 1 degree Fahrenheit, it's 1 degree Celsius. So I can click it from 24 to 25, or from 24 to 23. But each of those clicks is like a 2 degree Fahrenheit temperature change. I'd like to fine tune the temperature a little bit better. And so sometimes when I'm driving, it's like too hot at one and too cold at the other because it's such a big jump, Versus in the Fahrenheit, if I change it from 74 to 75, I can more fine tune it because it's a smaller step. Does that make sense for that? But let me ask you this. If the temperature is 0 degrees Celsius, what is the Fahrenheit temperature? 32, and I can use the equation to figure it out. You know, 9/5 this plus 32. If the temperature is 100 degrees Celsius, what's the Fahrenheit temperature? 212. Okay, what if the temperature change was 0 degrees C? So let's say one day it's this temperature, the next day it's the same temperature. So what did the temperature change? 0. The temperature didn't change. And so we have the same temperature. It's a 0 degree C temperature change. So if, let's say one day the temperature was 25, the next day it's 25 degrees C. Did the temperature change? No. So what's the temperature change? 0 degrees C. Okay, now I'm going to ask you, what was the temperature change in Fahrenheit? Was the Fahrenheit, if the temperature change in Celsius was 0 degrees C, what was the temperature change in Fahrenheit?
It was 0 change, but it was 32 or 32.
Yeah, right. So did you get that? The answer is it's a 0 degree Fahrenheit change. So if the temperature didn't change in Celsius, then the temperature didn't change in Fahrenheit. And so the temperature change was 0 degrees C. And that's because the two zeros match. Let's say the temperature rose 100 degrees Celsius. If the temperature rose 100 degrees Celsius, what was the Fahrenheit change? 180. Okay, so when we deal with temperature change, it's just using conversion factor. What is the conversion factor? The conversion factor is for every 1 degree C temperature increase, it doesn't matter where you start. I could start here. If I had a 1 degree C temperature increase, how much did the Fahrenheit temperature increase? 1.8. No. And so in that sense, we have two different equations when we're dealing with temperature. One equation is for ambient temperature. The other equation is for temperature changes. So that's where I was talking, or what I was talking about the other day. When I'm looking at delta T, I don't have to do the plus 32, or the minus 32, because a delta T in Celsius has the same zero as a delta T in Fahrenheit. They're both the same zero. If this is 0, that's 0. And so there's no offset there in the zeros. And therefore, I could just use this conversion factor here. In terms of Kelvin, they're the same size. So 1 degree C temperature change in Celsius is equivalent to 1 Kelvin because it's 100 over 100. So this is the slope. This would be the conversion factor that we use. So if I had a 5 degree Celsius temperature change, then it would be 5 times 1.8 Fahrenheit change. There's no offset there. Does that make sense? So we have to be careful. So if this were a 288 Kelvin temperature change, then I calculate it differently than an ambient temperature. So if this were a 280 Kelvin change, then it would be a 280 degree C temperature change, because a Kelvin increment is the same as a degree C increment. But this is an ambient temperature of 288. It's an ambient temperature of 288, then I have to calculate it. And so the degree C is 15 degrees C. Yep. And then I can convert it to Fahrenheit. So there's some exercises here. You can go through those. Okay, after temperature, we talk about proportionality and density. Density is an example of proportionality. We have other examples of proportionalities too. Miles per hour. You know, if you're going 60 miles per hour, then that's a proportionality. And proportionalities are intensive. It's just a ratio. And so it doesn't matter if you go 100 miles or 120 miles or 300 miles. You know, so the 60 miles an hour, if you're traveling that stays fixed. The distance you travel is going to depend. Those are extensive properties. And so proportionalities are intensive properties. And so if the density of water is about 8 pounds per gallon, you know, does it matter if you have 2 gallons? Does that change the density of water? If you have 2 gallons, would it be twice as dense? No, it's going to be twice as heavy. Heavy mass or weight is going to be extensive, but the density is intensive. So this is the density. We're going to skip all this stuff here. They call it proportionality constant. This is intensive. It just maintains the same ratio. So the density of water is 8 pounds per gallon, roughly, or 1 gram per milliliter, approximately. I mean, if we round it, this is like 0.99 something grams per milliliter for the density of water. Densities are typically expressed in grams per milliliter and grams per cubic centimeter. Density is temperature dependent because volume. You know, volumes can expand or contract with temperature, and so that changes the density. So we usually associate a temperature with that particular density. But if we look at room temperature, what are some typical densities that we'll look at? And so let's take a look at densities here. So if we look at the density of water, it's roughly the 2 sig figs 1.0 grams per milliliter. If you want a more precise density, then we need the temperature, and we'd have to look it up in a table, because the density of water is going to change. And so if we want something more precise for the density, we'd use a table like the table in experiment 1. Here. So let's say we're on room temperature, which is 25, let's say 0.0. The density of water is 0.99704. How many sig figs is that? 0.99704. Yeah, 5 sig figs. So we have 5 sig figs of precision here. So this is a pretty precise density. But sometimes we don't need to be that precise. And so if we don't need to be that precise, about what is the density? So if I did it to 3 sig figs, 4 sig figs I'd drop the 4, so it'd be 9970. 3 sig figs I'd drop the 0, so it'd be 0.997. But if I do this to 2 sig figs, then what do? I drop the 7, and then I have to round up. If I round this up, it's going to come out to 2 sig figs, 1.0 grams per milliliter. And so if I look at all these, you know, approximately what are they? To 2 sig figs, they're all going to be, you know, I got to round up. So 15, 16, let's go down here. And so even though the density of water changes a little bit, it's always going to be to about 1 or 2 sig figs. It's going to be 1 or 1.0 grams per milliliter. Now, if I need a very precise and accurate density, then I'm going to use this and to get more sig figs. But it depends on how precise you need to be. And so that's the density of water. The density of water is about 1. And it's a useful number to memorize. What about some other densities? So if the density of water is 1, then gold has a density of 19.3. So gold is about 20 times more dense than water. And so if a pound, no, let's see, not a pound. If a gallon of water weighs about 8 pounds, then a gallon of gold would weigh about 20 times that. And so a gallon of gold would weigh about 20 times 8 would be 160 pounds. So if you had a gallon jug of gold, is that going to be, can you carry that with one hand, you think? No, could you carry it with 2 hands? A gallon jug of gold at 160 pounds? Maybe. It's going to be pretty hard to carry, though, isn't it? 160 pounds of gold. And so it's about twice as dense. But is gold the most dense element on Earth? No, what is the most dense element on Earth? And about how dense is it?
You said it last.
What did I say?
I
Hmm?
forgot.
You forgot or I forgot?
I forgot.
You forgot? I have forgotten too. I know it's between osmium and IR, which is iridium. So I looked it up. I looked it up today because I forgot which one. They're close to one another. And so do you know the winner?
What was that you?
Let's take a look.
Wasn't it that one?
The most dense element is osmium. Osmium is the densest naturally occurring element. And how dense is it? It's a little more dense than gold. Uh-huh.
What makes things more dense than other things?
What makes things more dense? Because they're made up of atoms. And so some atoms are heavier than other atoms.
Yeah, but that's not the heaviest atom.
It's not the heaviest atom. That's correct. It isn't the heaviest atom. There are heavier atoms than it. But there's another thing that you have to consider in terms of density. And do you know what that other thing you have to consider?
It's volume.
Yeah, the volume. In other words, how the atoms pack together in the crystal structure. And so we see crystals of osmium here. And what we want to know is the arrangement of those crystals. So the thing is, if you have a box of oranges, have you ever tried to pack a box of oranges into a box? I mean, there are different ways you can stack them. So if we stack them like this, is that a good way of stacking oranges inside a box? It turns out this isn't a good way of stacking oranges because we're wasting a lot of space. This space is what we call empty space. And when we measure the density, we're measuring the entire box of oranges plus empty space. Like this. A better way of stacking the oranges would be like this. What we do is the next layer we offset a little bit. Here. And the next layer we offset a little bit. And the reason we do that is to reduce the amount of empty space here. And so the other thing it depends on is how heavy the oranges are and how much empty space we have in there. And in other words, the structure. We call this a structure. Did you know that? Okay, we know that the density of water changes with temperature, right? And so we need to know the temperature. But the structure is kind of amorphous and it doesn't really change much. But did you know that ice doesn't have the same density? Like, for example, the ice at the bottom of a glacier, underneath the thick layer of ice versus the ice at the top of a glacier is different. And it depends on how the water molecules pack together. And so
Aren't they like a crystallized solid?
Mm-hmm.
Like
They have different crystals. So the ice crystals at the bottom, under the sheet of ice, has a different crystal structure than the ice at the top. Do you know how many different ice crystals there are? We call these phases. Phases are different phases of ice. And think about it. At the bottom of a glacier, you have tons and tons of ice on top of it, crushing it down. And when it crushes it down, it can tweak and distort the structure. And so ice exhibits at least 19 phases. 19 phases depends on how the water molecules pack together in the ice lattice. And these are going to have different densities. So even though the water molecule weight doesn't change, all these water molecules weigh pretty much the same, how they pack together in the solid state changes. This is filling the box, and how well do you pack the water molecules in the box is going to dictate the structure. So ice, the biggest proportion of ice is going to be what we call just normal ice, like ice cubes. And ice floats on top of water, but maybe some of these will actually not float, but some of these might actually sink in water because they're more densely packed. And so that's the reason why. So osmium and iridium has a combination of good tight packing plus heavy atoms. That's what causes it to be the most dense. Now, the density is measured on the volume. If we measure the density of an atom, then that's a different story, but it's too hard to measure the density of a single atom. We can calculate the density of a single atom, and they're the heaviest ones. But a lot of these heavy ones are actually quite big, in diameter as well. So that would offset things. In fact, the lower we go down in the periodic table, the bigger the atoms become. And so if we look at the first one, the first row, the atoms are quite small, but when we get to the second row, they're about 4 times bigger. And when we get to about the third row, they're about 9 times bigger. And then we get to the fourth row, they're about 16 times bigger. And there's a little pattern there. Do you see the pattern? When we get to the fifth row, they're going to be about how many times bigger, would you guess, based on that pattern?
64.
If the pattern goes, think about this number pattern. 1, 2, twice as big, 4, 9. What would be the next number in that pattern? No, these are things science. You don't worry if it doesn't come up. It's 25. But if it doesn't come up, it's not a big deal. These are things, and these things take time to figure out. When you look at patterns, it's not so easy. Like here, if you look in science, the first thing is we take observations. So these are your raw observations here. Do you see a pattern here? You look at this table, do you see patterns? Some people, I think I told you, one of my students asked me, do I have to memorize this chart? This was in Chem 1B. I said, no, you don't have to memorize the chart. But you should know the patterns in the chart. You know the patterns in the chart? You see it? No, because it takes time. It takes time to figure out the patterns, right? It's not so easy. If it were easy, then like simple patterns, then anybody could be a scientist. You don't have to really worry about. And this is a job of scientists. And what makes science difficult is finding these patterns in nature. Sometimes they're glaringly obvious, sometimes not. But that's the scientific method. So this is ice. Do you see a pattern in these numbers? Let me show you. This is a density table of water. Yeah, we see some patterns here. So for example, we start up at 0 degrees C, and what's the density? This is just 6 sig figs, so this is a better, more precise table. And so at 0.0 degrees C, what's the density of water? 0.999843. Okay, this is just 6 sig figs. To 5 sig figs, what would the density of water be? 99984. To 4 sig figs, what would it be? 9998. To 3 sig figs, what would it be?
1.
1.00 to 3 sig figs.
Why does it lose 1 0 like everything?
Why does it lose 1 0 is because it's because of the rules for sig figs. Now the rules for sig figs have a problem. The rules for sig figs are supposed to represent what?
40 numbers.
Hmm?
40 numbers?
Well, yeah, they're all the numbers are kind of important, but the sig figs are supposed to represent what? Sig figs are supposed to represent precision, and precision gives us an indication of what? Hmm? Not the accuracy. Precision and accuracy are different, but kind of. You know, it could be a measure. There's another word I'm looking for.
Calibration?
No, calibration is referring to accuracy, and systematic error. I'm looking for something else. When we do sig figs, we do the plus or minus thing. What's all that plus or minus stuff all about? This is the stuff you should write in your own words. What is that plus or minus stuff all about?
Margin of error.
Hmm? The margin of error. What we call it is, in science, we call it uncertainty. You know, all these measurements have some degree of uncertainty, and so sig figs will tell us what kind of degree of uncertainty we have in the range of things. Now, sig figs is not the best way to handle uncertainty. You know what the best way to handle uncertainty is? The reason we use sig figs is because we could use algebra. And the algebra for sig figs is we count the sig figs and we figure out at the end how much we're supposed to have. Or when we do addition, you know, we just figure out how many decimal places we have. But the proper way of dealing with uncertainty is by using calculus. And this class doesn't have that prereq. You know, the prereq for this class is algebra. If we have calculus, then it wouldn't happen. If we use calculus, this would be to the 3 decimal places, 1.000, which gives us 4 sig figs, which violates the sig fig rules. But the violation of the sig fig rules is not a big deal because the sig fig rules are a simplified version of the calculus. So the sig fig rules are actually wrong. And so there are a number of cases where the sig figs gives you the wrong level of uncertainty in a calculation. In fact, let me just show you. So this is quite well known. So if you continue on to Chem 1A, you'll hit Chapter 1 of the Chem 1A book. In Chapter 1 of the Chem 1A book, you'll hit a problem like this. According to the rules on significant figures, the product of the measured quantities, 99.9 and 1.008 meters, this is how many sig figs?
3.
This is, when we multiply these two together, the answer should be expressed in how many sig figs? 3. So the answer should be expressed as 3 significant figures, 101 square meters. Yet, in this case, it would be more appropriate to express the result of 4 significant figures. And so we're going to violate the sig fig rules and express this in 4 sig figs. Why is it more appropriate? It's more appropriate because this is a more accurate reflection of the uncertainty that you expect in the number. And so this is like one of the first problems on sig figs in Chem 1A. And so right away we say, okay, the sig fig rules, yeah, they're easy to apply, but you might not get the correct answer. And so that's exactly what happened with the density table. You're right, it should be to 3 decimal places. That would be correct, but we'd have to introduce some calculus to talk about uncertainty. Calculus would be like the next level class after this. Then you do that. And it's called propagation of errors. So this is Chapter 1, Chem 1A. This is a little preview of Chem 1A. What's that?
Do you teach over the summer, Chem 1A? Do you teach over the summer, Chem 1A?
No. No, I don't teach summer.
That's
Okay.
your time off.
Yeah, but for fall. We're also going to jump and get another little preview of Chem 1A with a temperature problem. Is I talked about two methods of problem solving in chemistry. One, dimensional analysis, like 90% of the problems, 95% of the problems are dimensional analysis. Two, algebra, like 1% of the problems. And three, there's a third method for problem solving. And the third method for problem solving involves when we have two unknowns. Let's say x and y are both unknowns. Then how do you solve it? If you have two unknowns, you need... So most of the problems you do, you have one unknown. So you solve for that one unknown. Like in this case, what's the area? So length times width, area. But in some problems, we have two unknowns. In fact, in a lot of science problems, we'll have two unknowns. How do we solve for the two unknowns? X and Y. What have you done in algebra to solve for two unknowns?
Plug in zero.
Hmm?
Plug in zero.
Sometimes you can make an assumption that one is zero, but not always. Uh-huh.
So elimination? Like some sort of
Yeah, kind of eliminating one of the unknowns. How do we eliminate one of the unknowns? So if we had x and y, we got to get rid of one. Let's try to get rid of y. How do we get rid of y so we can just solve for x? Uh-huh.
I don't know if this is what you're looking for, but like sometimes you find like the similarities between the two, and then you see exactly where they're the same, and set them equal to each other.
Yeah, you could do that, but that's not the way we're going to do it.
Or like another way that I could think about was like if y is on one side and x is on the other, you can subtract y off of that side and then bring it over to the other side and then make it a zero, if that makes sense. So like for instance, like if it's yeah.
Yeah, but that doesn't work for all the problems. You can't always just subtract. We want something general that works for all problems. No, you don't really multiply both sides.
Make a system of equations.
Make a system of equations. Do you know the system of equations? System of equations is if you have two unknowns, you need two equations. And so what you do is one of the equations, you say, okay, you set that y equals this, and then do a substitution. Have you done that? Solve for one variable and then substitute. Yes? No? It turns out there are a lot of problems like that in science. So we're going to look at that today using temperature. And so we'll get to that later. A system of equations. All right. Let's go back to this here. So we need to know what the density is. The density is defined as mass over volume, and the typical units are not pounds per gallon. The typical units are grams per milliliter. So if that's the units, then what we want to know is the range. So what's the typical range? The reason we want to know the range is sometimes we don't want to come up with some ridiculous answers. So one of the things is on this in Chem 1A also they have to calculate the density of water, and this is a Chem 1A students. And some of these Chem 1A students will calculate a density of water of 480 grams per milliliter. Does 480 grams per milliliter sound reasonable to you? What's the densest element on Earth? Osmium, and how dense is it?
Like 22.
Like 22, 23 grams per milliliter? What is 480 grams per milliliter? There's no such thing. And that's because, you know why they get 480? Or weird densities like that? Let me show you why. You go back to this density table. Look at the first three digits. Do the first three digits change much? So let's go from here. 999. 999. It stays 999 pretty much until we get to here. So we go from 999 to 998. Do you see that? And so in the Chem 1A, to save space, they don't keep rewriting 999 because it begins with 999. And so in Chem 1A, this is what they do on the table, and this confuses a lot of students. The first one is 999,843. Do you know what the next entry reads? They get rid of the 999 and it's called 850. And what they're saying is the first three digits are the same, it's just the last three digits that change. So they go from 850 to 856 to 863. Do you see that? And so how did they get 480 for the density, the theoretical density? So they read the table and, was it 430? What is it? 480. Well, let's go with a different one. Let's say they got 442. You know, what was their mistake? They just read the last three digits and assumed that that was the density, 442 grams per milliliter. Does that sound like a reasonable density to you for water? This is water. This is not even osmium or whatever. No. And so what we want to do is we want to have some reference points so that we can see if something's ridiculous. Let's say somebody told you that they drove to San Diego and they drove at a speed of 1,000 miles an hour. What would you say? Well, there must be a mistake in how you read the gauge or a mistake in your calculation. You aren't going to be driving at 1,000 miles an hour. And yet, you know, what if I told you kilometers per hour? You know, okay, I was driving at 100 kilometers per hour down the neighborhood street. Is that reasonable, or am I risking a ticket? You know? Or 200 kilometers an hour. So what we need is some kind of reference points to see, is that reasonable or not? And therefore, we want to have some densities kind of memorized. We don't have to be so precise. So for example, the density of gold is around what? Roughly 20. You know, I just call it 20 because 20 is an easier number to remember. And then the most dense ones are around 22, 23. Okay. But those are a lot heavier than water. You know, that's 20 times heavier than water, 23 times heavier than water. So a gallon of osmium would be really heavy. But most solids, like, for example, copper, what's the density of copper, roughly? Well, from the last experiment was what, 8.56, was it? Or roughly what? We don't have to be that precise. You know, copper is about 9 times heavier than water. If we want to be more precise, then it was like 8.56 or something. This is actually incorrectly rounded, but about 9. Copper's pretty dense, lead's pretty dense, 11, silver's pretty dense. Iron, around 8, aluminum about 3 times. Most solids are around this range, you know, about twice as dense. Most solids sink in water and about twice as heavy as water, wouldn't you say? But there are some solids that are lighter than water, like wood. Wood, like pine, is half as dense. You know, oak is a hardwood, that's about 8/10 density of water, but they all float on top of water. How about air? Air is going to be a lot lighter than water. So if I had a milliliter of air, it's only 0.0012. This is 1.2 milligrams. Or what we say is this. It's about 1,000 times less dense than water, air is. The density of air, and for gases we like to use liters rather than milliliters. The density of air is 1.2 grams per liter. So I'd need 1,000 milliliters. make a liter, and so it'd be 1,000 times. Helium is 0.17 grams per liter. So gases we like to do in grams per liter, but everything else we like to do in grams per milliliter. Now, grams per milliliter is the same as grams per cubic centimeter, so those units are interchangeable here. So a centimeter cubed is exactly the same as a milliliter. So we can use those interchangeably. However, sometimes people like to use cubic centimeters for solids and milliliters for gases and liquids, but it doesn't really matter. Okay, so you want to know a rough range of densities. Okay, so then we go here. The mass of a 50.00 milliliter sample of methanol. How many sig figs is that?
3.
3?
It looks
No,
like
what did it
4,
be?
but
No, it would be 4.
It's 4.
It's 4. 'Cause
Yeah.
It's 4.
All the zeros after non-zero and a decimal are significant. So this would be 1, 2, 3, 4. 4 sig figs.
So I have a question.
Mm-hmm.
If it was just 5.00, it would be 3 sig figs.
Yes.
Got it.
Yeah. So the question was, if it were 5.00, it'd be 3 sig figs. So that's correct. It weighs 39.59 grams. How many sig figs is that? 4. So if we take the mass over volume ratio, which is the density, I should get how many sig figs? 4. But there's a problem here because how many sig figs is that? 4. How many sig figs is this? This is like 1, maybe 2. So if this were 1, that's not very precise, and that means we can only express the density in terms of 1 sig fig.
So then it would just be 8.
Yeah, it would be. We'd have to round this up. If we drop the 9, we're going to round that up to 0.8. And so, if this were just 50, we can't be this precise. We'd have to call this 0.8 grams per milliliter. But what they did was they made a mistake. This is a typo. This should have been written as 50.00, and that way we can get 4 sig figs here. Otherwise, we're not allowed 4 sig figs there. So this is measuring density. And is this more dense than water or less dense than water?
less dense.
This is less dense. So this should float on water, but methanol doesn't float on water because methanol is what we call soluble in water. And so methanol dissolves in water. And it dissolves pretty much to any extent. That is, methanol and water mix. It's like mixing water with water, which is different than mixing sugar cubes with water. When we mix sugar cubes with water, can you put an infinite amount of sugar cubes in water?
No.
So if you had a cup of coffee, what's the maximum number of sugar cubes you can dissolve in a cup of coffee? I don't know. We can measure it though, right? We can figure it out. But there is going to be a limit, right? There's going to be a limit because we can't dissolve any amount of sugar. But there are some things there's no limit. We can dissolve any amount of methanol in water because methanol and water are very similar in properties. And that's what we call miscible. It's like mixing water with water. Is there any limit to how much water I can mix with water? No, there's no limit. It's just water. And so methanol is so similar to water in that way, it does. But methanol does have different properties. So for example, I wouldn't want to drink methanol. You know what they call methanol? They call it alcohol. And so a lot of people like to drink alcohol, but you don't want to drink methanol. Because methanol is what's termed wood alcohol. And they call it wood alcohol because you can make methanol by fermenting wood. Do you know what wood is made out of? Wood is made out of glucose. Glucose, you know, glucose is sugar. And so wood is made out of glucose, which is sugar. And there are different ways to make alcohol. One way of making alcohol is by fermenting grains and sugar. Like when I was taking organic chemistry, we made alcohol. We made alcohol by getting a bunch of table sugar and yeast and water and mixing it together and letting it ferment. And a couple of weeks later, it generated alcohol. But it was a different kind of alcohol. It was called grain alcohol. And you know what grain alcohol is? The name for grain alcohol? It's ethanol. And ethanol you can drink. But methanol you shouldn't drink, because you know if you drink methanol, what will happen? You'll go blind or you will die. Yeah. And that's not an urban myth, that's true. And so don't drink methanol. The reason people ferment wood is because it's this cheap source of glucose. But the problem is it makes wood alcohol, not grain alcohol. And wood is a lot cheaper than sugar or grain, and so people are tempted to make it. And so let's talk about this. I guess I didn't. I guess I closed the tab. So we'll look at some methanol incidents here. Like in Australia, in 2013, 3 people died and 1 suffered partial blindness. This is permanent. It's not reversible. When they ingested a homemade beverage containing methanol. Homemade beverage, yeah, wood is a lot cheaper than sugar, so, but the problem is you make methanol. Not only that, you know, when COVID was going around, there was hand sanitizer, and some hand sanitizers use methanol. That's illegal now with the FDA. You can't have methanol in hand sanitizers. You can have ethanol, but you can't have methanol. People were trying to extract the alcohol out of hand sanitizers and drink this stuff, unfortunately. In Brazil, this is 1999, there have been more recent cases. 35 people died, 450 hospitalized. 49 people died in Cambodia, 300 were hospitalized. You know, there are some people, some tourists that went down to Mexico. Did you hear about that? A couple. This is last year, I think, or the year before. And they were at the bar, and they ended up dying in their room. And that was, some people were suspecting that might be methanol in the beverages. But government restrictions on liquor and beer sales during COVID-19 pandemic may have exacerbated the illegal production and sale of alcoholic beverages. So, methanol tainted drinks. So 35 people in 2020 died in Mexico. That was close, but let's go to Canada, or let's see, anything in Canada? No. But let's see in the US what we have. In 2018, a Massachusetts man died after ingesting alcohol that was contaminated with methanol. But this is kind of a tragic story because this person thought they were buying ethanol. The product consumed was labeled ethanol extraction, 95% and 5% water. This is what we made in the lab. So when I fermented the ethanol, it created a mixture of yeast and a whole bunch of other stuff. So what I wanted to do is I wanted to separate the mixture. One of the easiest ways of separating that mixture was by distillation. But distillation isn't perfect for ethanol. And so with ethanol, the purest you can get by distillation is 95%. They call this 190 proof? Is that 190 or 180? 190 proof, yeah. And so that's the purest you can get. And so this person thought they were buying moonshine or 95% ethanol. Unfortunately, it wasn't. And so since I fermented it myself, then I went ahead and took the risk of trying to consume it. This is up in the organic chemistry lab. So we collected it in a vial. I just wanted to taste it. Taste what 95% ethanol tastes like. And so I took a little sip of it, and you know what happened? It's so volatile, it just pretty much vaporized in my mouth into a gas, gaseous ethanol. So it was okay. It wasn't anything special, but it was kind of an interesting experience. But I knew what it was made from, and I knew, I could measure some of the properties. So, for example, I could see what the temperature was in the distillation apparatus, and so I could use those properties to determine it was ethanol. Methanol has a very different boiling point, and so if the boiling point were much lower, like 38 degrees C, I think is the boiling point of methanol, I wouldn't have done that. And so there are certain properties. Unfortunately, when you buy something, you don't know what it is. You don't know what's in that mixture, and it turns out that this person thought it was legitimately this, but it turned out it wasn't. So an FDA recall was issued, and the company is no longer selling the product, which was sold over the internet and shipped by the U.S. Postal Service. So it's still happening today. I think it was like 3 years ago in Chile, there were a whole bunch of deaths that were reported. These don't see much press, but they're continuing to happen. All right, so if you want something, you could measure its density, for example. So if you don't know what that liquid is, maybe the density will tell you. And if you're getting a density like this, then that's probably methanol, whereas ethanol has a pretty close density, so you gotta watch out. It depends on what your percent error is. So you might have gotten a density of 0.8 something, and you thought, oh, this is ethanol, right? But how accurate was your determination? You trust your work? If you're 5 or 10% off here, you could be thinking you're drinking ethanol, and in reality it could have been methanol. And so let's see what the density of ethanol is. .789. This is in different units. This is in kilograms per meter cubed, and so we'd have to move the decimal over. And so this would be 0.789 grams per milliliter. What would be the density of ethanol? 0.789 versus the density of methanol. Density of methanol is, come on, 0.791. Do you think your density measurements were so precise and so accurate to easily differentiate between methanol and ethanol? What would you say? Would you trust it? So I got my density was 0.795. And you go, okay, so 0.795 is closer to 0.791 than 0.789. Do you drink it? Would you drink it? I wouldn't. I wouldn't drink it. I'd need more. And you could get more data. I mean, there are other properties you can check and other things you can do. But the densities are a bit too close to differentiate the two easily. Whereas fool's gold and real gold, fool's gold, this density is around 7, 8, versus real gold, its density is around 20. So there, do you think you could do a quick density measurement to tell the difference? Yeah, that should be easy to determine. The density of a certain machine oil is 0.910 grams per milliliter. Find the volume occupied by 196 grams of that oil. So this is just dimensional analysis. This is the main problem-solving method. This is equivalency. We can come up with two ratios, milliliters per gram or grams per milliliter, just flip it over. And so in this case, we're going to use milliliters per gram. We're going to cancel out the grams and leave us with milliliters. Let's look at the sig figs. How many sig figs here? 3. How many sig figs here? 1,
Oh,
infinite. Whenever we have an equivalency like this, we like to say in exactly 1 milliliter, there's approximately 0.910 grams. And so this is infinite, this is 3. This is 3, so our answer should have 3. The fewest number of sig figs. So 215 milliliters. Is this more dense or less dense than water, this oil?
oil is.
This oil is less dense. Oil and water don't mix. Methanol and water mix easily. We call those miscible liquids. Oil and water are immiscible liquids. They don't like to mix together. And so this oil is going to float on top of water. There are some oils that are more dense than water that sink. And so it depends on how dense that oil is. Okay, that's the chapter 2 ends with chapter 3 ends with density. And so let's move on to chapter 4 next. Okay, chapter 4 talks about gases. So what we're going to have for the test is we're going to have chapters 1 through 4. The test is going to be next week on Tuesday, and the test is going to be mostly multiple choice with a few free response questions. The multiple choice, I'd like you to get a Scantron. Can you get the form 882 Scantron, which is the long
Is it the
green
green one?
one?
Okay.
And it has A through E. It's the narrow. It's the 882. Form 882. Scantron. We're going to need, you might want to go to the bookstore and buy a 6-pack of those. They also have them at the library. It's the A through E. There's 50 questions per side. So you're going to have some multiple choice questions. I'll probably post an old test, but the old test might not be exactly the same as your test. The questions might be a little bit different, and the balance of questions might be a little different. But we're going to have multiple choice. You can get an idea of what types of multiple choice questions I asked from the old exam, and some free response. I don't know how many questions are going to be on the test yet. The homework. So you're going to have homeworks for chapters 1 through 4, I think. Depends on how far through 4 I get on Monday, but it should be okay.
Do you want it turned in on a PDF, like online, or do you want it like in person?
Okay, do I want it as a PDF or in person? Either is fine.
Okay.
You could submit it as a PDF online. I'm going to put an upload link on Canvas to submit your homework. Or you can just hand it to me on paper, like this. If you have your homework in a notebook, then you can just keep it in your notebook and give it to me.
Okay.
And what I do with the homework is I just see if you attempted the problem. I mean, the answer, the solutions guide, and the answers are in the book. And so worst case scenario is you can just copy the solution from the solutions guide and turn that in. And so in theory, you should be able to get 100% on the homework. It shouldn't be difficult. It just takes time. Some people run out of time. They don't have enough time to even copy the answer and just turn in a lot of blank problems. If you leave it blank, there's going to be no credit for that particular problem.
I had a question about the test. Is it gonna be like mostly about our lectures, or like a very big mix of our lecture and lab?
It's mostly lecture, and then homework, and then lab. Yeah.
So the homework it's also included as part of like, the test,
Yeah.
like the
Some
practice.
homework style problems, right?
So like questions for like the slideshows will appear?
Mhm.
So like,
Yeah, that's a good question. Will questions from the slides appear? Yes. So you should be able to do all the questions that we do on the slides, or look at on the slides.
Well, like the, sorry, will like the milliliter, microliter, like all of that be included as well? Because I know that we briefly covered it, so I'm,
Yeah, all of that will be included. But not all the metric.
okay.
So the question is, will milliliters and liters be included? Yes. You need to know that 1,000 milliliters per liter. That one you should have memorized. Yeah.
But I'm talking about like the other unit measurements, like converting them, like will that be a big portion of this first exam, or is that going to be just a small portion?
The unit conversions are a big portion.
Okay.
The dimensional analysis. What conversion factors do you have to have memorized? The definitions you have to have memorized. So if I asked you to tell me how many microseconds are in a day, could you do that? No.
Well,
Well, maybe not right now, but you should be able to figure it out.
do a 60 times 60, then times 24.
Yeah, something like that. Yeah, you'd sit there
then
and
you
try to
convert
figure it
to
out.
micro.
Yeah, and then convert it to micro. So you'll be required to know some of those. All right, let's talk a little bit about gases here. A lot of these we've already talked about. Can gases be compressed? Yes. Can they be expanded? Yeah. Gases are compressible, and then you can also expand them. It requires work, though. To compress a gas, you have to do some work, and to expand a gas, you have to do some work, but it can be done. And it can only be done to a certain extent. Like, pretty soon, the amount of work it takes to expand or the amount of work it takes to compress is too much. And so we end up with an imbalance of levels, let's say. Okay. Liquids always like to rise to the same level. Have you ever heard that? Liquids like to rise to the same level. So if one level's higher, then it doesn't rise in this case. One will lower and the other will rise until they reach the same. But that didn't happen yesterday. You know, because when you had the flask underwater, did the liquid levels rise to the same level? No. You had to lift the flask up, right, or lower it down to get them to the same level. So we had to do that. Gases have low density. How low? Somebody asked you about how low the density of a gas is. What would you tell them? You tell them that gases are about how many times less dense than water? Or just approximate what order of magnitude of density is a gas, like air. Water is about 1 gram per milliliter. Air is about, you don't have to be super precise, but 0.001 gram per milliliter. So 1,000 times less dense. And so rather than expressing it in terms of grams per milliliter, what most people do is multiply by 1,000 and express it by the units grams per liter. And so water is about 1 gram per milliliter. Air is about 1 gram per liter. A little bit more, 1.2. But, you know, the density of air changes depending on the temperature. Hot air expands, cold air contracts, so the density can vary markedly depending on the temperature. Gases are easy to mix. Some things are hard to mix, like sugar cubes and coffee. You can't mix an infinite amount of sugar cubes, but in theory, you should be able to easily mix gases because most of the gases consist of empty space. Gases exert constant pressure on the walls of their container. So some of this stuff is, you don't have to worry about memorizing these point by point. We just need to have a little bit of practical knowledge of the gases. And so this is in terms of macroscopic, this is in terms of particulate. And so this is trying to put more weight on here, more force to push it down. So this is going to compress the gas. So we have compressed gas. When we compress the gas, we get rid of some of the empty space here. And it requires some work, so we need more weight here to push it down. We can remove some weight and the gas will expand here. And we can remove all the weight and it'll expand a little bit more. But when we remove this weight, is there still weight on the lid? Yeah, what is the weight on the lid? So if I remove this copper, then what's weighing down on the lid here? Air. And how much does air weigh? 14.7 pounds per square inch. So even if I remove this other copper weight here, there's still 14.7 pounds. It'll expand a little bit because it weighs less. But what I can do is, yeah, there's 14.7 pounds pushing down, but if I lift it up, I can get less. And so by lifting it up or pulling it up here, exerting a force upwards here is going to cause this to become a vacuum. And we'll have less. The vacuum just means it has a lower pressure than atmospheric pressure. Atmospheric pressure being 14.7 pounds per square inch. Here's it at the macroscopic level. Iron is about how many times more dense? You know, you don't have to know the number, but is iron as dense as copper? No, iron's less dense than copper. Is iron more dense than water? Yeah, so it's somewhere between 0 and 9. It's more like 8. And so the iron sinks. This is water. Water has a density of about 1. And this is air in a balloon. And air consists of nitrogen and oxygen. They don't show the oxygen there. Gases are easy to mix. So here I have these red, and then I introduce these greens here. There's lots of empty space, so there's room. But even though there's room, it still takes work to mix those. It takes work because over here, you know what causes pressure? What causes pressure are collisions between the gas particles and the wall. And so the force of the collisions will cause pressure. And the greater the force, the greater the pressure. So over here, I have 3 reds colliding with the wall. Over here, I have 3 reds and 3 greens colliding with the wall. And so over here, we say that this is double the pressure of this. But we can still mix it. Because of the motion of the gas particles, they can collide with the walls on any surface. The top, the sides, the bottom. They're just moving in random motion. And so what we see is we see equal pressures here. However, for liquids, it's going to be heaviest down here. So if you're weighing the liquid here, it's going to be the heaviest because you have the most molecules stacked on top. If you go a little higher, it's going to get a little lighter. Higher, it's lighter, and at the top, it's going to be the lightest, right? Because you don't. This is like being in a swimming pool. If you are in the swimming pool and you swim to the bottom of the pool, do you feel the weight of the water? Yeah. If you're like in a 9-foot swimming pool, you're going to feel the weight of the water. It's going to weigh a lot. So not only do you have the weight of the air, it's 14.7 pounds, but you also have the weight of the water. How much does water weigh? If I wanted 14.7 pounds of water, how tall does it have to be? In other words, if I had a tube of water and I wanted to get 14.7 pounds, how tall does that have to be? Well, that's about 2 gallons of water. If I had a 1 square centimeter tube and I wanted to put 2 gallons of water in it, how tall would that be? You know how tall it'd be? It'd be about 30 feet tall. And so if you could swim 30 feet underwater, then you have double the pressure. That is, you have about 15 pounds. Actually, you have triple the pressure, I think. Or was it double? No, double the pressure. You have 15 pounds of air, and then 30 feet would be about 15 pounds of water. So you'd experience 30 pounds of weight on you. Will you feel it? Have you ever swam 30 feet underwater? No, but you would feel it. You'd feel 30 pounds of weight on you. We call it 2 atmospheres. So you'd be at 2 atmospheres of pressure. What was that submarine that went down? Ocean Gate. Did you hear about that? How deep was that? It was really deep, going to the Titanic. And you got to think, how many pounds of water was that? That was a lot. You know, I don't know how many atmospheres. Each atmosphere is 15 pounds.
It said they reached 12,500.
12,500 feet. And so every 30 feet is 15 pounds. So that's 12,500 divided by 30. Let's just do a quick calculation. 12,500 divided by 30. That's 416 times 15. 6,250 pounds of water per square inch. Plus 15 pounds from the air above it, because there's still air pushing down on the top of the water. So that's plus 15. So 6,265 pounds per square inch. It's huge. I mean, even when I go to 9 feet underwater, it's too much pressure for me. I can really feel it in my ears. So anyway, let's take a break here, and then we'll start again. 15. All right. The characteristics of gases at the particular level can be described using kinetic molecular theory. Kinetic molecular theory just comes from the quantum mechanics of matter. Anyway, kinetic molecular, this is kinetic is motion, and molecular refers to molecules, but not everything forms molecules. So, for example, helium forms atoms as particles. Neon, the same thing, atoms. So molecules is just used loosely here. So it should be kinetic particulate theory instead. But we just use molecules to represent things, whether they're atoms or molecules or particles. It's okay, but gases consist of particles and empty space. The volume occupied by the particles is negligible when compared to the volume of the space they occupy. So this room is filled mostly with empty space. So if I take all the air in this room and cool it down into a liquid, you know, how many milliliters of liquid would I have? And, yeah, it would be a very small amount of liquid. And so it goes to show it's mostly empty space. These other ones, some of these we worry about later. Attractive forces among molecules of a gas are negligible. Don't worry about that. We're going to talk a lot more about that later. The average kinetic energy of a gas particle is proportional to the temperature. We've talked about this. Temperature is a measure of the kinetic energy. Molecules interact with one another in the container walls without a loss of total kinetic energy. This just means they collide with the walls and each other, and they don't slow down. So here's a visualization of this, of the particulate nature. So if we look at this with some scanning microscope, we'll see like 100 water molecules. These are going to have vibrational, rotational, and translational motion. So these are all moving about. But there's always, even though there's some water molecules coming in and some water molecules leaving, there's always going to be about 100 water molecules. That's because the water molecules are touching each other. Over here, this is gaseous water, or water vapor, and most of the time it's empty. Then once in a while, a water molecule will pass through. It's moving very fast, but you might get an image of that. And so these are little snapshots at a very zoomed in particulate level. The pressure is defined as the force per area. And so F is the symbol for force, A is the symbol for area, so it's just force over area. And what is the force? It's the force of the collisions. And so the pressure is generated by the force of collisions of the gas particles. So these rapidly moving molecules of a gas collide with the surface, generating pressure. The factors that influence the pressure of a gas is the volume. If you squeeze the volume smaller, you have less space. If you expand the volume, so expanding and contracting the volume will change the pressure. The amount of gas, if you put in more gas into the container, you're going to get more collisions. Smaller volume, more collisions. Higher temperature, you'll have more frequent collisions, and the collisions will have higher impact energies. And so higher temperatures means they're moving faster. Lower temperatures, we're going to lower the pressure. Higher temperatures will increase it. We can measure the air pressure here by a barometer. Did anybody have a chance to read the barometer yesterday? No. Okay, you may want to go over there and play with the slides and look at the Vernier scale. But basically it works like a balance. We measure the weight of the air outside. What's the weight of the air outside? 14.7. And then what we're going to do is, this is imbalanced here. The weight of the air is greater than the weight of the vacuum. But the vacuum doesn't weigh anything. But we make this balanced here. And so we have the weight of the air is going to equal the weight of the liquid mercury. So if you want to get what we call 1 atmosphere, that is 14.7 pounds of water above you, how deep do you have to go underwater? About 30 feet deep. But if you were to swim in a pool of mercury, you don't have to go that deep. You just have to go about 760 millimeters deep, and then you can swim under 14.7. So 14.7 pounds of mercury, which is equivalent to 760 millimeters of mercury, weighs 14.7 pounds, but that would be equivalent to 14.7 pounds of water. But you need a lot more water because water is a lot less dense. Since water is a lot less dense, you'll need about 30 feet. And so if you made a barometer out of water, you'd have to make it 30 feet tall to get the two weights equal. So on the one side over here, we'd have the air, the weight of the air. On the inside here, we have the weight of the water, but water is not very dense, so this has got to extend way up there, 30 feet. Does that make sense for that? And so making a water barometer isn't going to be very practical for measuring things like atmospheric pressure. We call it atmospheric pressure because 14.7 pounds is the average pressure at sea level on a sunny day. So some of the properties that we want to measure for a gas are pressure, the force per unit area. And one of the ways we can measure pressure is by measuring the room pressure using a barometer. And then we do a process called equalizing pressure. Equalizing pressure, do you remember lifting up the flask or lowering the flask to get the two water levels equal? So what we did there was we made sure that the pressure inside the flask is equal to the pressure outside the flask. That is the pressure in the sink. And when those two are equal, then we know what the pressure of the gas inside there is the same as the pressure outside. And so we did that, and then we can just read the barometer. It gives us the pressure. The volume changes. When you push the flask deeper in the water, the volume gets compressed. When you pull it out from the water, the volume expands. So we've got to get just the right volume. And so this is why we got the two levels equal, and then we plugged it just to get the just the right volume of water in the flask here, or the right volume of air. And then the amount we didn't measure. This is the number of gas particles in the sample. There are different ways we can measure that. And then the temperature, we measure the temperature of the gas. So those are the properties or characteristics of the gas that we want to know. So when we do the pressure, there are different pressure units that we could use. One of the most common pressure units are ATM. This is normal atmospheric pressure is 1 ATM. 1 ATM is about 760 millimeters of mercury worth of pressure, which is 14.7 pounds. And this is by definition. And so this is your average pressure, and we'll just define that as normal pressure. And so 1 ATM is defined as 760 millimeters of mercury. So we'll make that a definition. So how many sig figs is that? Infinite. So this is infinite sig figs. Just add one more line here. It's exact. Now, a torr, sometimes it's inconvenient to talk about millimeters of mercury. It's much faster to talk about torr. So 1 millimeter of mercury is exactly 1 torr. And so these are exact. So 1 atmosphere is exactly 760 millimeters of mercury, and that's exactly 760 torr by definition. Well, this is not the international unit. The international unit of pressure is the Pascal. The Pascal is in units of something called newtons. Newton is a unit of force. It's Newton per meter, per square meter. That's a Pascal. So 1 ATM is equivalent to 101,325 newtons per meter squared. A newton per meter squared is called a Pascal. And so 101,325 pascals. So the normal average pressure is 101,325 pascals. Exactly. And so this is also exact. Here. So do you want to use pascals? Do you want to remember this? Not really. We can make it a little easier to deal with by using bar. 1 bar is 10,000 pascals exactly. And so if 1 bar is 10,000 pascals, then this is 1.01325 bar of pressure. And so in the USA, we like to use atmospheres. In the rest of the world, they like to use bar or millibar. You know, so sometimes on the weather report, you'll hear how many millibar the pressure is. And so how many millibars is this? This would be 1,013.25 millibar. So normal pressure is 1 atmosphere, or 101,325 pascals, or 1.01325 bar, or 1,013.25 millibar. That's normal atmospheric pressure, 1,013.25 millibar. But those aren't so convenient to remember. You know, so what we say is that 1 atmosphere is approximately 1 bar. You're going to be off by 1%, 1.3%, 1 part out of 100. You'll be off by. So the reason it's not so convenient, the reason why I still prefer atmospheres is because, you know, what's normal atmospheric pressure? 1 atmosphere. That's in atmospheres, but what's the normal atmospheric pressure in bar? 1.01 325. Do you want to memorize 1.01325 if somebody asks you what normal pressure is? No, normal pressure is 1.01325 bar. And so this is why the U.S. sticks with atmospheres. However, Petrucci is published in the rest of the world would be Canada. So Petrucci likes to use bar. And so we have to get comfortable using both bar and atmosphere. It's easy to do the conversions, do conversion factors here. So 1 bar is 10 to the 5th pascals, or sorry, 100,000. Is that right? Let's see. Yeah, sorry. Yeah, that's right. Not 10,000. I said 10,000 earlier. It's 100,000. 100,000 pascals, or 100 kilopascals. So that's a bar. And the normal atmospheric pressure is 101,325 pascals, or in terms of kilopascals, I don't know. In terms of bar, it's 101,325 bar. It's normal. These are all by definition here. These are all exact. These ones aren't very useful. Sometimes we'll use kilopascals. Like I bought a bike tire and they had the pressures in kilopascals, so I had to convert it to kilopascals. Kilopascals are common in Europe, I guess. So this one we don't have to memorize. These ones we should memorize here. Let's get rid of that. This next one we don't have to memorize here. 1 atmosphere is also 29.92 inches. This is not exact. How many sig figs is this? This is 4 sig figs. And I don't memorize this because this one's easy to derive. Normal atmospheric pressure is 760 millimeters of mercury. And then we're going to go from millimeters to what? We're going to go from millimeters to centimeters. So in 1 centimeter, there are 10 millimeters. And then we're going to go from centimeters to inches. Do you know the conversion from centimeters to inches? What is it? 2.54. Oops, I got it upside down. Let me flip this over here. 1 inch goes on top, and then 2.54 centimeters goes on the bottom here. And so the millimeters cancel, the centimeters cancel, and that leaves me with inches of mercury. And over here, how many sig figs do I have in 760? You'd normally say 2, but you should know that 760 is by, what's normal atmospheric pressure? 1 atmosphere. 1 atmosphere is how many millimeters of mercury? 760 exact by definition. So this is infinite sig figs. How many sig figs in 1 centimeter per 10 millimeters? Infinite. And then how many sig figs here in this last one? No. 3 is wrong. You'd like to say in exactly 1 inch, which would be infinite, there are approximately 2.54 centimeters. But it's not approximate. It's by definition. And if something's by definition, how many sig figs do we have? Infinite. So this is infinite sig figs. This one you have to memorize. there's exactly 2.54 centimeters and exactly 1 inch. There's no uncertainty there. And there's no uncertainty because it's by definition. This is normal pressure by definition. And so this gives us 29.92 inches. Let me do this. You don't have to memorize 29.92 inches. But you should be able to derive it. Because all we're doing is converting from millimeters to inches. That's only 4 sig figs. We can go further, because we're allowed infinite sig figs, so I can carry as many digits as I want for the answer. In this case, it was just rounded to 4. And so this is not exact. How about this? Is this exact? Exactly 14.7 pounds per square inch. Now, this one, we're just going to say approximate. So this one, we'll just do 4 sig figs here. I was giving you 3 sig figs. I was just calling it 14.7. It might be exact by definition, but we'll just call it 4 sig figs here. I probably should look it up. All right, so we have some other pressure measuring devices. We have the barometer, and this is another one, the manometer. The manometer and the barometer kind of work similarly. So let's talk about that here. So we have the seesaw relationship here. We have outside here, this tube is open to the air. So what's weighing down on this side? The air. And how much does the air weigh on a normal day? 14.7. But is every day a normal day? No, it fluctuates. So this is why we have a barometer mounted on the wall. We have a barometer mounted on the wall so we can see these fluctuations in the air pressure. Like, for example, yesterday, did anybody write down the air pressure I measured yesterday? I think it was like 758.4 millimeters of mercury. If it's 758.4 millimeters of mercury, is that a little bit lower than normal or a little bit higher than normal? 758 higher? It's actually a little bit lower because normal is what? 760. So it's a little bit lower than normal. And so whatever it is, if it's a little lower than normal, that's the pressure that's pushing down on the outside. So the pressure pushing down on the outside fluctuates. We use the barometer to measure it. It's not always 14.7. Look at the pressure inside. Which one weighs more? The gas A, the atmosphere, or the gas G, this yellow gas here? Which one weighs more? The gas G. The G weighs more because if you look at the seesaw, it's highly tilted. And so if they both weighed the same amount, it would be horizontal. But since G weighs more, it pushes it down, and then we get this imbalance in levels. So gas G is sitting on top of the mercury here. Gas A is sitting on top of the mercury here, which is the air, the atmosphere. And so for sure the gas G weighs more. What we're going to do is we're going to do a little thought experiment. What we're going to do is we're going to equalize the levels. If the seesaw is horizontal, then both sides weigh the same amount. And so over here we have gas G weight on this surface. Over here we have the air plus this mercury. So what we do is we swim underneath the mercury until we get to this level, and then we feel how much this weighs. How much does this weigh? Well, we're not actually going to weigh it. What we're going to do is we're going to measure how many millimeters of mercury this is, because we know that normal atmospheric pressure is 760 millimeters of mercury, and then we add this many millimeters of mercury weight to the 760, that gives us the total weight on this side. And so what we do is we set them equal. That is, we want the left side to equal the right side on this balance here. And so in order to do that, we get that the pressure of the gas, this one, is equal to the pressure of the air up here, plus the pressure of this liquid mercury here that's pushing down on there. And so that's plus the pressure of the mercury liquid. And so we end up with this equation here. Now, what if the gas weighed less? Like this. So you have the gas sitting over here, and you have the air sitting over here. Which one weighs more? The air weighs more. And so what we're going to do is we're going to do this hypothetical experiment where we bring this horizontal. Now, if this is horizontal, both sides weigh the same amount. So on the right side here, we have the weight of the air. On the left side, we have the weight of the gas, which isn't enough, plus the weight of the liquid mercury. And so we set up an equation similar to what we just did. On the left side, we have the weight of the gas plus the weight of the mercury. On the right side, we have the weight of the air. Now we're solving for the weight of the gas or the pressure of the gas. The pressure of the gas, we just do a simple subtraction, is equal to the air pressure minus the mercury. Here. And we end up with this equation here. But either way, it's the same thing. We're just solving for the P of the gas. Over here, the left and the right. It just so happened the P of the gas was isolated over here. Made it easier to solve for. That's what we call the manometer. This is the open-ended manometer, and it kind of works like a balance. Let's look at an example of a problem here. The pressure inside a steam boiler is 1427 psi. Express this pressure in atmospheres. So we just take 1427 psi and we use this conversion factor here. 1 atmosphere is 14.70 psi. This is 4 sig figs here. If this were exact, I wouldn't put the 0 there. I'd just say it's exactly 14.7. That would be infinite sig figs. So the reason I suspect this is only 4 sig figs is they put one of the zeros, because an exact number has an infinite number of zeros after it. And so this is 4 sig figs, this is 4 sig figs. Our answer is allowed up to 4 sig figs. So 1427 psi is about 97.07 atmospheres to 4 sig figs. The pressure in an automobile tire is 29 psi. Okay. What we have to do now is go back. I need to talk about gauge pressure versus absolute pressure. Gauge pressure is the pressure above atmospheric pressure. Absolute pressure is the sum of the gauge pressure and the atmospheric pressure. Well, what does that mean? So let me show you an example of what that means. Let's say you're going to go buy a tank of helium to fill up some balloons. So you go and buy this tank of helium. And you try to fill up a balloon. So you open the valve and no helium comes out. So you return the tank and you say, this tank doesn't have any helium in it. But the person that sold you the tank says, you're wrong, it does have helium in it. It does have helium in it. But it won't come out. Why won't it come out? It won't come out because the helium inside there is at a pressure of 14.7 psi. But the air outside here is at a pressure of 14.7 psi. So if the air pressure is 14.7 psi and the helium pressure is 14.7 psi, then they're equal and opposite and no helium comes out. What we need is we need a higher pressure here to force the helium out. So the person that sold you the tank says there's helium in it. What you have to do is you have to put your lips on the stem here and suck the helium out. And then you can blow up the balloon. Do you want to do that? No. And so, unfortunately, you don't know how much helium you bought. What you need to know is you need to know what the pressure of the helium is. Because you just bought a helium tank that has 14.7 psi of helium in there. And so this is our gauge. And our gauge is reading 14.7 psi. And it's not going to come out. It's not going to come out, so you have to suck it out to get it down to 0 psi. Because once we're at 0 psi, are there any collisions? There are no collisions. And so what we have here is, this is called gauge pressure. No, this is not gauge pressure, sorry. This is absolute pressure. Let me redo that here. This is called absolute pressure. The problem is you aren't going to get it down here, because do you think you're going to be able to suck out all the helium out of the tank until it's truly empty? Because if you were to suck out all the helium out of the tank to get 0 psia, 0 psia means there's no collisions in here. In other words, there's no helium. If there's no matter inside this container, what do we call it? A vacuum. And this would be a perfect vacuum. And so what we need is we need a vacuum pump to suck out all the remaining helium here. But we have to be careful, because if there's no pressure inside here and there's about 15 pounds of pressure outside here, you know what could happen? We could get an implosion. And that's when we have an imbalance of pressure. So if the helium tank probably can't withstand 15 pounds. Maybe it can, I don't know, of pressure. But it might start to crush. That being the case, we have something called gauge pressure. And so rather than representing the pressures in absolute pressure, we can represent the pressures in terms of gauge pressure. And so when the helium hits 14.7 psi absolute, no more is going to leak out of the container. And we aren't going to be able to fill any more balloons. So we call this 0 psi G. 0 psi G just means that the tanks run empty, because nothing's leaking out, but it's not truly empty, because there's still some helium in there. In order to get rid of that, we need to crush this down to nothing, to all the heating, or we need to create a perfect vacuum in here. We can do that. We can suck it out. So we hook it up to a vacuum, and then what happens to the pressure? What happens to the pressure is we can start sucking it out, and the pressure is going to drop. And then we're going to hit the absolute zero pressure here, which is going to be minus 14.7 psi G. If we get to minus 14.7 psi G, that means we're at 0 psi A, which means there's no gas in here and there are no collisions, and therefore there's no pressure. But since this is an arbitrary zero here, this is just where it stops leaking out, then that's what we have for this. So let's say you're driving in a car and you get a flat tire. When you get a flat tire, you measure the pressure of the tire and it's reading 0 psi. Is that reading 0 psi A, or is that reading 0 psi G? It's reading 0 psig. To get the remaining air out of the tire, you'd have to suck it out, and then it'll crush in. Like, what was that submarine called? Ocean Gate. It would crush in like the Ocean Gate, if you want to get all the air out. So now let's go back to this problem here on the PowerPoint. The pressure in an automobile tire is 29 psi. Is that psi-A or psi-G? If this 29 psi goes to 0, does that mean you sucked every last air molecule out of there? You couldn't even suck, even if you had a powerful vacuum, it's hard to do. And so this is psi-G. Because if this goes to 0, it's not truly empty. There's still air in there. It's just not enough to inflate the tire. The weather report states that the barometric pressure is 30.09 inches of mercury. How would you report the absolute pressure in the tire to a colleague in kilopascals? Okay, so let's break this problem down into different steps. The pressure is reading 29 psig. If the pressure goes to 0 psig, is there still air in the tire? Or did we suck out all the air? There's still air in the tire. How much air? How much air in the tire is, we say 14.7, but is every day 14.7? No. Some days are a little higher, some days are a little lower. On this day, do you know what the pressure is? The pressure is 30.09 inches of mercury. This is the pressure of the atmosphere, P sub A, call it, or the air pressure. Let me make sure that's correct. Yeah, 30.09 inches. All right, so what that means is that when this gauge is reading 0 psig means that the pressure of the gas inside there is equal to the pressure of the atmosphere, so that there's no movement. The gas doesn't want to come out, and the gas isn't forced in. It's not forced out or forced in. It could diffuse back and forth. And so when we have 0 psig, that means we're at 30.09 inches of mercury here. In order to go to absolute 0 pressure, we need to go from 30.09 inches of mercury to 0 inches of mercury. And then we've sucked out all the air out of that tire. But what we're going to do is we're going to try to get the same units. So what I'm going to do is I'm going to convert this into PSI here. So let's go ahead and do that. 30.09 inches of mercury. The first thing is I'm going to convert it from inches to millimeters. So I know that 1 inch is equivalent to how many centimeters? 2.54 centimeters. And this is exact. So the inches cancel. And then I know that there are 10 millimeters exactly in 1 centimeter. So the centimeters cancel. And that gives me millimeters of mercury. And then I know that in 1 atmosphere, there's exactly 760 millimeters of mercury. So the millimeters of mercury cancel, leaves me with atmospheres. And then I know that there are 14.70 psi per atmosphere. 1 atmosphere. And that will get me psi. So let's convert the inches of mercury to psi. .09 times 2.54 times 10 divided by 760 times 14.7. That gives me 14.78. How many sig figs am I allowed here? 4. And so I'm going to carry 1 extra digit to lower what's called rounding error. And so this is PSI. Is this PSI A or PSI G? This is PSI A. And so at 0 PSI G, I have 14.782 PSI A. And so that means that at 0 PSI G, I'm going to have to suck out all this, which means it's going to be minus 14.782 PSI G. So in order to suck the remaining gas out of here, I'm going to have to go down to minus 14.782. Now, there's no such thing as negative pressure. And so this means at 0 psig, there's still gas in there, and there's still collisions. And so this negative just means it's below 0 psig. So this is negative 14.782 psig. And that means if we're at 29 psig, what must we be? We must be at 29 plus 14.78. So we'll get 29 plus 14.78 psi. So plus 29, that's going to give me 43.78. 43.78 psia. .782 psia. So 29 psig is equivalent to 43.782 psia. But they want this in kilopascals, so we're going to have to do some more calculations here. So we'll go with 43.782 psi, and then we're going to convert that into atmospheres. It's 14.70 psi per atmosphere. And then we're going to convert this into pascals. There's 101,000, you don't have to memorize this, 325 pascals per atmosphere. And then we're going to convert this into kilopascals. There's 1 kilopascal is equivalent to 1,000 pascals. And so let's go ahead and calculate this. 43.782 divided by 14.7 times 101,325 divided by 1,000. And I get 301.789. How many sig figs am I allowed? Kilopascals. I'm allowed 4 sig figs, it looks like, so I'll round this to 301.8 kilopascals. that would be the absolute pressure at 29 psig. Uh-huh.
Is the 2 a subscript to 14?
The 2 is a subscript because it's just my notation. It's a way to keep track of sig figs. So I carry extra digits to prevent rounding. I'm only allowed 1 rounding step at the end. And so I carry extra digits to lower the round-off error. But the extra digits I subscript to tell me that those aren't significant. Those shouldn't be part of the sig figs. Okay. So the book did it. They got a 300 kilopascals. They did it differently, though. You could there are a lot of different ways you could do this. They went from psi to kilopascals directly. I didn't. So do this. All right. The next thing we're going to look at are some simple laws for gases. One of the laws is the volume and temperature relationship. So this is the raw data here. And so in science, what we do is we take our observations, and then what's the next step? We look for patterns. Do you see any patterns in this data here? Sometimes it's hard to see the pattern, so what we do is graph it. And so the experiment is this. What they're looking at is they're looking at the volume versus temperature. And the way they're looking at the volume is they're putting a mercury plug in here. And this mercury plug can go up and down. So if they heat this up, the volume expands. If they cool this down, the volume contracts. So it looks like they're cooling it down, the volume contracts because of the mercury plug. And they measure the distance, the height of the mercury plug. Well, the height of the mercury plug is not actually a volume, but it's related to the volume. And the height is going to be directly proportional to the volume, so that's why they're using the height rather than the actual volume here. This volume should be in millimeters cubed, or milliliters, or some other cubic centimeters, some other volume unit, but this is okay because they're going to be directly proportional. And we're looking at the relationship here. And so they plot out the temperature and the volume, and they come up with this. Do you see this is fairly straight line relationship? So we'll draw a straight line through those data points. And then they'll try to define this mathematically. If we define this mathematically, then we come up with this equation. Let's see if we can get this to work. This might be at the end of its life. Okay. Maybe it's not going to work. I have to resort to this. So this is a Scantron that you need to get here for next week's test. So we can represent the pattern there by a mathematical equation. This would be the most concise definition. So we need y. Y is going to be the height there, but in reality it's the volume. The volume and the height are directly proportional, so we'll just use the volume. The volume is equal to the slope, m. What is x? X is the temperature in degrees Celsius plus the intercept. What is the intercept? The intercept, we'd have to draw this line further until we hit the y-axis, right? And so we'll need to get that there. And so this is the form here, and I'm not going to complete this form, but when we have a mathematical equation that defines the pattern, and this mathematical equation is pretty consistent, you can see here with this data, and if we have some additional data, it seems to fit the line, then we call it a law. And is this law an empirical law or a theoretical law? What's the difference between an empirical law and a theoretical law?
Theoretical law, it's about what could happen in various situations without like being contradicted. But empirical law, it's only through the observation.
Theoretical law, so empirical law is what can be predicted. Is that what you said? And theoretical is what can or comes from empirical observation?
Well, it does come from empirical observation.
Well, maybe a little twist on that definition. Does anybody else have a definition? The difference between an empirical and theoretical law? The difference is where they come from. Where does an empirical law come from?
Experiments.
Experiments and observations. Empirical law comes from observations. Where does the theoretical law come from? The theory. Now, was this law derived from the theory of chemistry, or was it derived from observations? Observations. So this is what we call an empirical law. And this is what's called Charles' law, named after Charles, who studied this. Now, Charles' law, this is in terms of degrees Celsius. So this is Charles' law in degrees C. However, one thing is that happens is this. We can extend this line further, but it doesn't make sense to extend this line further in a certain sense, because what's the smallest volume you can achieve? So let's say I'm going to buy some liquid, any liquid like coffee or something, by the milliliter. And so I asked them, what's the smallest I can get? And what is the smallest you can get? So the smallest you can get is a cup of coffee, let's say. But can you go smaller than that? Yeah, half a cup, quarter of a cup, an eighth of a cup. Can you go smaller? Yeah. And so we can go smaller, maybe 1/1,000,000th of a cup. But what's the absolute smallest I can get? 0. Now, could I go negative? Is it possible to go to negative volume? So, no, it's impossible. We can't. And so the theoretical limit of volume is 0. We can't go below 0. Because once we hit 0, there's nothing there. And so if that's the case, then this is the theoretical limit of temperature, where it intersects here at 0, the x-intercept. Do you know what the x-intercept is in degrees Celsius? What does it look like? Looks like it's between -200 and -300. And what does it look like to you? It looks like, to me,
Just 75?
yeah, maybe like -270, something like that. But if we had more markings on here, I could be more precise. And so if I had more graduations, I can pinpoint this. And you know what it is? It's -273.15, 15 degrees C. So at -273.15 degrees C, the volume of the gas went to 0. We can't go below 0. There's nothing there. And so this is the theoretical limit of temperature. The theoretical limit of temperature is -273.15 degrees C. And then Kelvin comes around and calls that 0, because since we can't get any colder than that, we might as well call that the rock bottom temperature. The rock bottom temperature would be 0 Kelvin here. So if this is 0, if this is in Kelvin, then we can do the equation again. In degrees C, it's that. In Kelvin, what is the intercept? So if this is 0, then we have this as our y-axis, and the intercept here is 0. So at 0 Kelvin, we have 0 volume. And so what we end up with is an equation that looks like this. Volume is equal to the slope times the temperature in degrees C plus the intercept. The intercept is 0 here. And so we end up with this. Volume is equal to a constant. The slope is a constant times the temperature. This is called Charles' law in Kelvin. This is Charles' law in degrees C. We can arrange this like this. We can go V over T is equal to a constant. So this is Charles' law. And then we could say, if we change the temperature, what happens to volume? So what we can do is we can do this. We can go V initial over T initial is equal to V final over T final, which is equal to a constant. So the ratio is a constant. This is an intensive property. This ratio doesn't matter how much you have or what temperature it is. It's always the same ratio. It's intensive. This is a proportionality. And so this is Charles' law in Kelvin. Over here, we have to do some extra stuff. This B is 32. And so what we end up with is Charles' law in terms of degrees C is this. V initial over T initial in degrees C plus X. Well, let's see. No, not 32, sorry. This is going to be plus 273.15 is equal to V final over T final plus 273.15. And so this is Charles' law in degrees C. So probably the easiest thing to do is to memorize or use Charles' law in terms of Kelvin. And then if we're given degree C, we just convert from degree C to Kelvin so we can use a simpler equation here. And so let's take a look at yesterday's lab. Since my pen's not working, I'm going to just use the data from this morning. See if I still have my data from this morning. All right, this is from one student from this morning. Their thermometer, do you think that's very accurate? their boiling water came out to 105.6. Did they just have especially hot boiling water, or do you think their thermometer was improperly calibrated and is reading too high? What do you think?
I mean, ours also read 105.
Yours also read 105? Anybody get close to 100? You guys got close to 100? These are mass produced, so they're off. Normally when we use these thermometers, we calibrate them first. Boiling water, under normal conditions, should boil at about what? 100. Yesterday's pressure was close to 14.7, so it should have been close to 100 degrees C. So it's reading, this thermometer was reading about 5 degrees too high, basically 5.6 degrees too high. But that's okay, because what we do is we use the same thermometer for the cold water. And what we're looking for is a difference in temperature. So it doesn't matter if the hot one was reading 5 degrees high and the cold one was reading 5 degrees high, then the difference, those two errors cancel each other out, right? And so we're not going to calibrate the thermometer. Both of these are an error. It's called a systematic error, but the systematic error is eliminated when we look at the difference in the temperature, which is okay. So their cold water was 27.7, and then the volume of water entering the flask, they got 88 milliliters, and then they measured the volume of the flask with the tube and the stopper, and they got 476 milliliters. That would be the volume of hot air, which occupied the entire container. So the volume of the cold air is equal to the volume of everything, the whole flask, minus the volume of water that got stuck in there. And so that would be 476 minus 88. This gives us 398 milliliters. This is the experimental volume of the cold air. What we're going to do is we're going to use Charles' law to calculate the theoretical volume of cold air. And so that's what's being done here. We're going to use the Kelvin version of Charles' law. The Kelvin version of Charles' law is V1 over T1 is equal to V2 over T2, which is equal to a constant. And then what we're going to do is we're going to solve for V2. V2 in this case is going to be the volume of cold air. V1 will be the volume of hot air. Okay, so we're going to rearrange this equation, solve for V2. V2 is equal to T2 divided by T1 times V1. So what I need to do is I need to convert to Kelvin in order to use the equation. So I'm going to go 27.7 plus 273.15, and then 105.6 plus 273.15. So I'm going to use the Kelvin temperatures in here. And then I have my V1, which is 476 milliliters. And I calculate a volume based on Charles' law of 378 milliliters. So based on calculation and the temperature drop, my new volume should have been 378. The volume that was measured was 398. So the volume that was measured we call the experimental. The volume that we calculated we're going to call theoretical. And so when we calculate the percent error, assuming the calculated volume is correct, then that's going to be experimental minus theoretical divided by theoretical times 100%. So we're going to get 398 minus 378 is going to be 20 divided by 378 times 100. And that gives us 5.3% error here. What do you think about 5.3% error? Is that too big or is it okay?
Too big.
It's kind of big, but when you consider the experiment, there's lots of potential error. You know, the potential error comes in a lot of forms like, did you cap it tightly enough? Did any air leak through? Did you submerge it? Did you submerge it long enough? So it turns out that 5.3% error is pretty good. What I've seen is like 500% error. If you get 500% error, what do you think? It's not very good, but I've seen it. I've seen huge errors in this experiment. Huge errors, I don't know what happened. You know, maybe they got a lot of air leaked out, maybe the stopper came loose. They barely got any water sucked in there. And so when they measured it, it wasn't like 88 milliliters, it was like 5 milliliters, 10 milliliters of water. Or sometimes the water, you know, accidentally leaks in. or whatever. So you'll see what your trial 1 is, and then you could do trial 2 and then see what the percent error is. We're going to use the Kelvin version because the Celsius version of this is this, but essentially this is the Celsius version. Do you see that?
Yeah.
And so it's just converting the temperatures. Now, not only are we going to do this calculation, this is a Charles law calculation, but we're also going to do some additional calcs. Do you see, this is the Celsius version. And in order to convert Celsius into Kelvin, how much do I have to add it to it? 273. But what we have is we have the data. We know what T1 is in Celsius. We know what T2 is in Celsius. We know what V1 is, and we know what V2 is. So we know these. So what we're going to do is we're going to calculate the experimental 273.15. So I'm going to use some algebra and solve this for x for trial 1. And then I'm going to solve this for x for trial 2. I already know what x is supposed to be, but I'm going to use my data to see what it comes out to. The expected x value should be 273.15. Is that what I calculate here? Probably not. It's going to be due to experimental error. And so that's going to be another Charles law type calculation. And the last Charles law type calculation, I'm going to graph this here using this graph paper on the report sheet. So let me rotate this here. So I know what the hot is, 105.6. I know the volume, 400 whatever it was. And I know the cold was 20 something, and the volume here. So I have 2 points, and then I'm going to assume that this is linear. And what's the smallest volume we can have? 0. So I'm going to see where this line hits, 0, the x-intercept. And hopefully it hits around here, which is minus 273.15. Hopefully. But, you know, sometimes I see people have to add another sheet here. They add another sheet and make a whole bunch of blocks because the temperature it hits over here is like minus 450. I've seen more than 450. I've seen minus 600. I've seen lots of them, lots of different ones. And that's just due to experimental error. And so hopefully it comes out to minus 273. Let's see what yours comes out to. So we're going to draw 2 lines. Trial 1. Hopefully it comes out to minus 273.15, and trial 2, hopefully that comes out to minus 273.15. And so we're going to get the x-intercept, and then you're going to write it here. X-intercept, hopefully minus 273.15. Trial 1, minus 273.15, trial 2. The expected intercept is minus 273.15. And then we're done with this lab report. All right, any questions on this? So we're going to have one more quiz today. I see a lot of people already finished this dimensional analysis quiz. Since a lot of people finished, let me give you another problem to do here. And this other problem is going to be a bit of a challenging problem. Let me tell you. First, I'm going to do an example of it, and then I'll let you do one. So the 3 common problem-solving techniques. 1, dimensional analysis, to string together conversion factors. 2, algebraic equations, Celsius, Fahrenheit conversions, ambient temperature. 3, 2 unknowns. Two unknown problem. This is going to be an example of a two unknown problem. 76. A Fahrenheit and a Celsius thermometer are immersed in the same medium. At what Celsius temperature will the numerical reading on the Fahrenheit thermometer be? Let's do B. Twice that on the Celsius thermometer. And so they're asking for the Fahrenheit and the Celsius temperature. And so this is for B. So I don't know what the degrees Fahrenheit is equal to, and I don't know what the degrees Celsius is equal to. So I have two unknowns. If I have two unknowns, I need how many equations to solve it? Two equations. I already know one equation. What's one equation for this? One equation is degrees Fahrenheit is equal to 9/5 degrees C plus 32. So that's one equation. But this equation has two unknowns. I need one more equation. Can you think of one more equation for this? And the one more equation is going to be this. The Fahrenheit thermometer will be twice that of the Celsius. So the degrees Fahrenheit, this is the other equation, degrees Fahrenheit is going to equal double the degrees Celsius. So let's say the Celsius were 100. That means the Fahrenheit must be reading 200. But it's not the case, because if the Celsius is 100, the Fahrenheit's 212. But since the size of the Fahrenheit and the size of the Celsius are different, there could be a match here. And so let's figure out, there's only one temperature that this happens at, if at all. So when we have two equations like this, then what do we do next?
You make them equal to each other?
Yeah, we do substitution here. And so we'll do substitute this for degrees Fahrenheit. 2 degrees C is equal to 9/5. You know what 9/5 is? 9/5 is 1.8 degrees C plus 32 degrees. And then I'm going to subtract 1.8 from both sides, 1.8 degrees C. So I'm going to get 0.2 degrees C is equal to 32 degrees. And then the degrees C is equal to 32 divided by 0.2. 32 divided by 0.2 is what? 160. So if the Fahrenheit is double the Celsius, that means the Fahrenheit, degrees Fahrenheit must equal 2 times the 160 degrees, which is going to give me 320 degrees. So when the Celsius is reading 160 degrees, the Fahrenheit will be reading double that, 320 degrees Fahrenheit. We can check this, and so let's do a quick check. The quick check is, let's calculate the degrees Fahrenheit based on this Celsius. So the degrees Fahrenheit is 9/5, 160 degrees plus 32. So I'm going to go 160 times 9 divided by 5 is 288 plus 32. So 288 plus 32 is 320. So it's a match. It checks. And so at that temperature, at 160 degrees, the Fahrenheit will be doubled. All right, so why don't you try A, number 49. At what temperature will the Fahrenheit be reading 49 degrees less than the Celsius? Okay, this will be the quiz here for today.